Today I'm going to talk about deep neural networks. We've looked at neural networks with hidden layer, input layer, hidden layer, output layer. And now we're going to ask the question, what about adding more hidden layers? What are the pros and cons? So the goal is to see the advantages and disadvantages of deep neural networks. And it's basically weighing representational power versus vanishing or exploding gradients. So let me get into that. So how many layers should our neural network have is a question that you could ask yourself. Recall the universal approximation theorem that I described before. And it basically says that given any function you want, you can get arbitrarily close to modeling that function with a single hidden layer. That's great. The problem is, so we really only ever need one hidden layer. But is that the best approach? In terms of the number of nodes or the learning efficiency, no, we can actually usually do better. So if the number of nodes we have in our hidden layer is n, then it can be shown that such a neural network with a single hidden layer might require an exponentially large number of hidden nodes. Okay. So a deeper network is sometimes preferred. In fact, in the exercises, I run an example that shows you that for particular, like just a very simple learning example, you get a more accurate solution if you have more hidden layers than a single hidden layer. Same number of hidden neurons, but it's split into multiple layers and it learns more quickly. So it's actually good to have multiple hidden layers. It allows each hidden layer basically transforms your data to a different representation, and that can help in the learning process. You could argue that that's how our brains are so good at creating these abstract models of the world. I would almost argue that the intelligence of a species or even of an organism is based on how deep the neural network is. Because every time you add a layer on top of the neural network, you basically create another opportunity to abstract out and re-represent the information about the world. And ultimately, we don't care about photons entering our eyes. We don't care about the specifics of the light. What we care about is the objects that we're looking at. What are objects? Like a table or a stylus. It's a bunch of atoms. But when I see the light coming to my eyes from the stylus, my brain is interpreting it. It's sort of turning this sort of light impulses into nerve signals that go through multiple layers of my visual cortex. And eventually, I sort of abstract out from the shape and the color and the depth cues that it's a stylus. And that's relevant to me because using a stylus has relevance to my survival and my well-being. Hey, I get paid as a professor, so being able to recognize and use a stylus so I can teach my class and then make money, this sort of example kind of took a sinister turn. But anyway, I do get paid for my job. It's a great job to have. I'm very lucky. Recognizing the functions of chairs and other people and food and things like that. These are all abstractions of what you take in your visual system and your auditory system and your other senses. So, deep neural networks allow us to abstract information and re-represent it into a format that's more functionally useful to us. So, then why don't we use really deep networks all the time? Maybe the deeper you go, the better it'll be. So let me introduce one problem. It's a very famous problem, the vanishing gradients problem. Suppose the initial weights and biases in your network were large enough that the input current to many of the nodes was not too close to zero. As an example, consider one of the output nodes in this neural network. So let's say that this particular output here, jumping around. that input, that'll be Z, we'll call it Z1 for layer 3. So layer 0, 1, 2, and layer 3. So let's say Z1, 3 equals 5. So the input current to that particular output node is 5. And let's say it's a logistic node. So then Y1 is sigma of that, which is 1 over 1 plus e to the minus 5. And that equals about 0.9933. So therefore, dy1 by dz1, 3 is y1 times 1 minus y1, getting close to me here, which is about 0.0066. So that's a small number. Because the input current was so high, the derivative is small. And let me demonstrate that in a plot. So let's do the plot down here. So let me draw the logistic function here. Got an asymptote at 1 here, and I'm just going to say the bias is 0. So we're kind of looking at a curve like this. So when Z was 5 way over here, you see that we're really close to 1 way up here. But importantly, the slope is really small. Slope is approximately 0 over here, and way over here too. Slope is approximately 0. And it's only in this sort of region, sort of the sweet spot in here, where the slope is not too bad. So this is the sweet spot where the slope is much bigger than 0. Okay, so comparing this example up here, where the slope was 0.0066, let's say the input current was 0.1 instead. Instead of the input current being 5, the input current was 0.1. So in that case, y1 equals sigma of 0.1, which is 0.525, according to my calculations. Therefore, dy1 by dz1, 3 is, again, y1 times 1 minus y1. Just plug the 0.525 into there, and you get 0.249. So this is almost 40 times bigger than this. So just because of what the input was, the slope changed, the order of magnitude of the slope changes drastically. And it's because if your input current is large, you're out in these flat wings where the gradient, where the derivative is small, versus being in that sweet spot where the derivative can be much different from 0. So hence the updates to the weights will be smaller when the input currents are large in magnitude. So what about the next layer down? Let's say we're going to go even deeper, and suppose that the gradient on that the gradient of the cost with respect to the input current to the output node was 0.01. So let me write that down. Suppose the gradient with respect to Z3 of E is about 0.01. So what if the inputs to the penultimate layer were around 4 in magnitude? So from our output layer, we've got, fairly small derivatives. What about the layer below? Let's say the input current to the next layer down was around 4 in magnitude. Then all the corresponding slopes of their sigmoid functions would also be small. So in particular, sigma of 4 is about 0.982. So therefore, sigma primed at 4 is about 0.0177. So easy calculations to do. And so let's do a step of backprop and take this gradient and push it down through this layer here. Okay, so recall that the gradient at layer 2 is equal to sigma primed of Z2 Hadamard times the gradient at layer 3 times the weight matrix transpose. So I'm calling this W2. I usually label the weight matrix according to the layer it's coming from. It doesn't really matter, as you'll see. Okay, so I've already established that the derivative of the activation function in the next layer down was about let me do it this way, about 0.0177 times the gradient from the layer above is 0.01 times the weight matrix transpose. So in other words, let me do it this way. This whole thing, the gradient to the next layer down is about 0.000177 times the connection weight matrix. So the connection weight matrix can be whatever, but we're multiplying that by something really small. And this is just because the input currents were big enough that we were out in these wings, out in the flat parts of the sigmoid function. So this gradient gets smaller and smaller as you go deeper into the network. When this happens, learning comes to a halt. Learning comes to a halt because the gradients are so small that the updates to the connection weights and biases are tiny. And this is even worse. This gets even worse the deeper you go in your network. So this is called the vanishing gradient problem. Okay, now is a good time for a little joke break. So a man is at the doctor's office. He's getting some results from his doctor, and the doctor says, "I've got some bad news and I've got worse news." And the man says, "Oh boy, okay. Well, tell me what the bad news is first." The doctor says, "Well, the bad news is that your disease is terminal and unfortunately you're going to die from this disease and you've only got 24 hours to live." The man says, "What? That's the bad news? That's horrible. What could possibly be worse than that? What's the worst news?" The doctor says, "Well, I've been trying to contact you since yesterday." Okay. So another way to look at this vanishing gradient problem is you can actually observe it in a very simple neural network, just with one node per layer. So here I've got 5 layers. Well, 1, 2, 3, 4, 5 layers, including plus an input layer. And each layer just has one node, and so there's only one weight and one bias at each layer. So these are the weights. And these are the biases. Okay, so let's start with loss on the output side of E, Y, T. So the gradient with respect to the input current of the output node is, I'll just say Y minus T. So we're using one of those combinations of like linear output and mean squared error, or maybe we're using cross entropy with logistic, whatever. So using backprop, we can compute a single formula for the gradient of the cost with respect to the input current to layer 4. So that would be, let's see, Z4 is this input current into here. Right, so we have our gradient at our output our top gradient. So that's the gradient with respect to the input current here. Now we have to push it down a layer. So backprop says, well, you push it through the weights, so it'll be times W4, and then through the activation function. Okay, going deeper, I think you can see the pattern that at every layer we add another set of these. Okay, so going all the way down, we get y minus t times W4 sigma primed Z4 times W3 sigma primed Z3 W2 sigma primed Z2 W1 sigma primed Z1. Where's Z1? Yeah, that's input current down here. Okay, so that's fine. We actually have now computed the gradient all the way down to the gradient of the cost with respect to the input current to the first hidden layer. So let's look at the Z primes. What is the steepest slope that Z primed, sorry, that Z, what is the steepest slope that sigma of Z takes? So this is a logistic function. So as you know, it's you could be rewritten like this. So of course, sigma is between 0 and 1. In fact, it's strictly between 0 and 1. So if you were to plot that, it's actually just a parabola. And it's got a root at 0 and 1. And in between, it attains its maximum at 0.5. And this maximum, whoops, missed. Come on. This maximum is at 0.25. Okay, 1/4 is the maximum slope that the logistic function takes on. So, all else being equal, the gradient goes down by a factor of at least 4 for each layer, because the largest sigma prime can be is 1/4. So obviously the weights are going to have to be bigger to compensate. I'll get into that a bit later. So we can see this if we look at the norm of the gradients at each layer. So in the exercises, I've got various demonstrations of this. But if we just look at the kind of the sum of the squared gradients at each layer, I'm writing it like this. So this is just adding up over the different gradients, di E by di Z, the layer I, element J squared. Just square them and add them up. So for this particular example, excuse me, I've got output Y and input X, and then we're feeding up through the layers here. In this particular example, why do I say 5 layers? 1, 2, 3, 4. Okay, 5 layers including the input. You can see that I'm showing just for a given sample that I input, I compute the gradients going back down. And you can see I list all the gradients themselves, but I'm also showing you the 2 norm, the squared 2 norm. And you can see they start reasonably sized, but they get smaller and smaller and smaller as you go down, down, down. Same number of nodes, 4 at each layer, but they're getting smaller and smaller in value. And this is just because I don't know what connection weights I chose, but the connection weights aren't big enough to sort of compensate for the factor of 1/4, 1/4, 1/4 that the sigma primed lays on it at each layer. So this is the vanishing gradient problem, and it makes it difficult to train deep neural networks. The deeper a neural network is, the longer it will take to train, because the gradients get smaller and smaller as you go down into the network. Okay, there's also something called exploding gradients, as if vanishing wasn't bad enough. There's also exploding gradients. So it's a similar, though less frequent phenomenon, and it can result in very large gradients. So let me unpack this for you. Imagine I've got this neural network with a whole bunch of nodes, layers, each layer with one node again. Now I'm going to set up a particular state. So let's say the input was 1/2. Let's say this weight is 8, and the bias for this connection is going to be -4. Okay, so the activity of 1/2 times 8 gives me a 4, but then you subtract off the bias of 4, or add the bias, which is -4. So the input current to the next layer is 0. Okay, run 0 through a logistic function, you get 1/2. Let's say the next one is also a weight of 8 and bias of -4. You get input current of 0 again. And you can see we can set this up all the way up the network so that the input current at each layer is 0. And therefore the activities are 1/2. And we run this through a bunch of layers until we get to y on the output. Okay, big deal. So let's just start with some, I don't know, whatever, some value for the input current, the gradient of the cost with respect to the input current up here, Z. Let's see, this is 1, 2, 3, 4, 5. Okay. Now, using our backprop formula, to go down a layer, we multiply that by the connection weight. And then we multiply to get our die E by die Z4, we multiply by that connection weight and then times the derivative of the activation function. I'll just color in there. It's a derivative of the activation function. So that derivative is 1/4 here, right? Because it happens to be the input current was 0, which is the steepest part of the logistic function where the slope is 1/4. So that means that when we multiply by the weight was 8, but the slope of the logistic function was 1/4. Put those together, you get a factor of 2. So we basically have multiplied our gradient by 2. And you can see that for every layer we go down, we're multiplying by 2 because it's the same story. Our connection weight is 8, and our activation function, the slope of our activation function, is 1/4. So multiplying those together, you get times 2 times 2 times 2, all the way down. So therefore, the gradient of our cost with respect to our input current to the first layer is, let's see, 2, 4, 8, 16. 16 times the gradient at the top layer. So this situation is more rare since it only occurs when the weights are high and the biases compensate so that the input current lands in the sweet spot of the logistic curve. So when your weights are big but they're centered on the logistic function, you can get this exploding gradient problem. So when you're training deep neural networks, you need to be aware that some activation functions, many activation functions, have sort of this maximum slope. And if the weights are too small, you can get the smaller and smaller gradient as you work your way down through the network. Or if your weights are big, you can actually get growing and growing and growing gradients through your network. In fact, I suppose you could get both happening in a single network. Some gradients are getting really small and some are getting really big. I'm not sure about that. So these are things you should be aware of: the vanishing gradient and exploding gradient problems.